All right, in our second to last section of Chapter 5, we're going to be talking about something called integration by substitution, and it's the formal method for what we've been doing when we're undoing the chain rule. So whenever we undo the chain rule, if we had like sine of 2x, for instance, we've just been kind of winging it. Like, oh, okay, I see my correction factor should be 2, so I'll balance it out with a 1/2. Well, integration by substitution is an official method that we have steps for. It's a pattern that we will follow a certain set of steps and it will work out every single time, rather than the guesswork that's been involved with undoing the chain rule. Okay, so this is going to seem pretty familiar when we start with the chain rule stuff. So chain rule in reverse is what we're looking at here. And one thing, that little paragraph that I wrote up at the top there, it's very, very important to remember that we will never reach a point where we can integrate everything. We reached a point in first semester where we could take the derivative of anything we wanted, but that will never be true with integration. It's nowhere near as straightforward as derivatives are. Okay, so the derivative of the cosine of x to the fourth. All right, we're going to set up what that derivative would look like and kind of talk about all the pieces involved. So if y equals the cosine of x to the fourth, when we take the derivative, y prime equals, and we start with the derivative of cosine. Cosine's the main function. Derivative of cosine is negative sine. Then we leave the x to the fourth in place. You always leave the nested function nested. And then multiply by its derivative. So you've got a 4x cubed. And then, of course, you'd be likely to kind of clean that up. But what I want to point out is all of the pieces that you've got present there. Okay, so this first piece is the inside function, the nested function. And then this is the correction factor. Oops, probably could have said function. Okay, so we've got the nested function and we've got the correction factor. Not very good letters there. Okay, so when we see those pieces in an integrand, we know that we can do chain rule in reverse, which before, like I said, we had just been kind of winging it and just hoping that it worked out. So if you have an integrand that looks like this, undoing the chain rule, if it looks like this, negative 4x cubed times the sine of x to the fourth, and then of course dx, we could find the integral, because you've got all the pieces we need. We've got a main function, which would be sine, negative sine technically. We've got a nested function, and then you've got the correction factor in there. What we talked about with chain rule is that the correction factor doesn't need to be there exactly, but a constant multiple of the correction factor needs to be there. Okay, so our theorem, the substitution method, it's going to give us an exact step-by-step method that we can use. So if you see this, if you see the integral of f of u of x multiplied by u prime of x. All right, so if that's what you see in front of you, if you see a main function with a nested function in place and then multiplied by the derivative of the nested function, which is exactly what you have up here. Sine is our function f of x, x to the fourth is our function u of x, and then 4x cubed is our function u prime of x. If we see that, then the antiderivative is just this. Okay, where capital F, remember, is an antiderivative of f. Okay, so I should probably make that note. Okay, so capital F is an antiderivative of f. Okay, and you can kind of picture it. When you take the derivative of this, capital F prime gives you lowercase f of u of x, and then times u prime of x, and you'd land right back there. Okay, so that's our theorem. First example here. These ones are going to be set up very, very nicely. So what you're looking for is a function that has a nested function, and then you want to find the derivative of the nested function somewhere in there. Okay, so what we're going to use as our nested function is the x squared minus 9. In this, it just requires a keen eye. Once you get used to these, you will be able to spot what the nested function is very, very quickly. Because you need to look for two things. You need to look for a function that looks like it's physically nested, and then you need to find its derivative in there somewhere. Okay, so the x squared minus 9, what I mean by physically nested is it looks like it's plugged into another function. It's plugged into a square root function in the denominator. And then the derivative of x squared minus 9, 2x, is right there as well. Okay, so we've got the pieces that we need. So the x squared minus 9 is u. The 2x is u prime. We've got both of the pieces that we need. And this is the notation that we're going to use. And this is going to seem a little weird, but like I said, once we get going on these, it'll be second nature. So we start by writing our u substitution. U equals x squared minus 9. Okay, and then the notation that we're going to use is going to look like this. If we want the derivative, we're going to write it like this, du by dx. Okay, and that just means the derivative of u with respect to x. We're just going to use that notation instead of u prime because we want to be more specific and show that the variable we're using is x. So du by dx equals 2x. Since we're doing substitutions, the point is to rewrite this entire integrand all in terms of u instead of in terms of x. So we'll be able to sub out the x squared minus 9, we'll be able to sub out the 2x. The issue is we'll still have a dx there. So the reason we use this substitution, this notation, is because we'll be able to sub out the dx. So this becomes this. We multiply both sides by dx, and we get 2u equals 2x dx. So if you look at the original integrand, the 2x dx, we're going to replace it by a du, and then the x squared minus 9, we're going to replace it with a u, and then we'll have the entire integrand rewritten. Okay, so let me show you what it's going to look like. Integral of, so I've got u in the denominator under a square root, so I'm going to write it as u to the negative 1/2. That's what it means to be in the denominator under a square root. And then the 2x dx, this substitution tells us we can replace it with du. And now it looks like an incredibly simple integrand based on the substitutions I just made. This has to be a du because it has to match our variable that we're using in the integrand, which is why we had to make this substitution right here. Okay, so now let's take the antiderivative of this. Very, very simple. Much more simple than the one we started out with. So I start with u. My power pops up 1, up to 1/2. Then I divide by 1/2, so I end up with a 2 as my coefficient. And then I always have a plus c because it's indefinite integration. Now, we don't care about u. We just use that as kind of a means to get to my answer. So in your final answer, you always sub the original function back in. So 2, and then u to the 1/2 is the square root of x squared minus 9 plus c, and that's your final answer. Okay, and you can always double check that you would land right back here, because I promise you would. You just have to take the derivative of this, and you'd end up with 2x over the square root of x squared minus 9. Okay, so that is our basic method for substitution. All right, so I am going to show you how it works in example 2 again. So remember, the two things that we're looking for are the nested function and the derivative of the nested function. Okay, so the function that looks like it's physically nested is the x to the 4th plus 4x. So we see that right here. There's our u. U prime is 4x cubed plus 4. So it's not there perfectly, but it's a constant multiple right here. This is a quarter of what we're expecting our correction factor to be. We're expecting it to be 4x cubed plus 4. So this is a constant multiple. It's good enough. And I'll show you how we're going to play around with the coefficients. Okay? So we write down, and I want to see these things written down every time. You write down u equals x to the 4th plus 4x. And then our derivative, du by dx, is equal to 4x cubed plus 4. Which, if we start to simplify it a little bit, because you know what we started with, so we know what we need to sub out. This is 4 times the quantity x cubed plus 1. Now this is where we start to manipulate this equation a little bit to get what we need, to get what we started with over here. Okay, so the first thing we're going to do is we're going to multiply both sides of the equation by dx. So du would get replaced with 4 times the quantity x cubed plus 1 times dx. So now looking in here, we have something very close to that. We have x cubed plus 1 dx. We don't have 4 x cubed plus 1 dx. So we just divide both sides by 4. Okay, so we have 1/4 du is equal to x cubed plus 1 dx. Okay, so now we've got enough information to sub out everything in terms of x and replace it with stuff in terms of u. Okay, so the x cubed plus 1 dx, we're going to replace it with a 1/4 du. And the x to the 4th plus 4x, we're going to replace it with a u. So let's do our next round where we replace that entire integral. Okay, so this piece right here becomes the cosine of u. So I'm going to write that. And then the x cubed plus 1 dx, this line right here tells me that I can replace it with a 1/4 du. Anytime you're dealing with constants, you can just throw them out front. So 1/4 du. So that is my new and simplified version of the integrand, something that I can take the derivative of, antiderivative of pretty easily. Okay, so that's what I'm going to do. 1/4, the antiderivative of cosine is sine, positive sine, of u, and then I always have a plus c. And for my final answer, I am going to rewrite u back in terms of x. Okay, and you can always take the derivative of that expression again, just to make sure you end up with this in the integrand, and you will. Okay, another one. Example 3. Here, this is kind of a simpler one. All right, we've got a 4x minus 1, which appears to be our nested function, and you don't see anything there that looks like the derivative. But the 4x minus 1 is such a simple function, its derivative is just a 4. If your derivative is just a constant, you can manipulate it, just like we did in the example up above. Okay, so let's still start to set it up here. Okay, so now here's something that I want to point out that we're going to do in this next step when we take the derivative. Here we had du by dx, we ended up multiplying both sides by dx in the next step. Here we had du by dx, we ended up multiplying both sides by dx in the next step. So we're just going to go right to that step. Instead of writing du by dx and then multiplying by dx, we're just going to start with it. Okay, so we're going to write du equals the derivative of this, which is 4 dx. Okay, so here's what we have so far. This 4x minus 1 can get replaced with a 4x, or with a u, right here. U equals 4x minus 1. And then the dx, we want to replace the dx with something. So divide both sides by 4, and we'll be able to replace the dx. Okay, so now I can use this line and this line right here to rewrite this entire integrand in terms of u instead of in terms of x. Okay, so square root of u, which I'm going to write as u to the 1/2. And then the dx, this line tells me I can write it as 1/4 du. Okay, and like I said, anytime that you have a constant, just put it out front. Okay, so my antiderivative, I have this 1/4 out front, times u, the power pops up to 3/2, and then I divide by 3/2, so I multiply by 2/3, and then of course I have a plus c. So let's balance out those constants, sub back in my u, and I'll have our final answer. So this reduces down like this, and I'll have a 1/6 out front, and then I'll have the 4x minus 1 to the 3/2 plus c. Okay, so that's my final answer there. So hopefully this procedure is getting more and more familiar. We've got a few more examples on the back page that we're going to look at. And then the next lesson, we will have kind of a more advanced technique. All right, so 3 more examples here, and this will start to go relatively quickly. So this one is a little bit weird. We've got secant squared x times tangent x. Okay, and this, the way that it's written right now, we could actually go one way or the other. We could use tangent as our u, because its derivative is secant squared, or we could use secant as our u, because its derivative is secant tangent. So both the pieces are kind of there, because remember what you're looking for is you're like, all right, here's my substitution, and my correction factor is right there. So one way or the other, it's probably easier to just use tangent. So if we use u equals tangent, then that means that for du we have the derivative of tangent, secant squared x, dx. Remember on the previous page we talked about how instead of writing du by dx and then just multiplying by dx in the next step, we're just going to write it like this. It's kind of saving ourselves a step. And so you can see everything is right in there perfectly. All right, so we just make a very quick substitution. So the integrand becomes tangent gets replaced with just the letter u, and then secant squared x dx just gets very cleanly replaced with a du. So you can see how perfectly simple that integrand just became. All right, so for the integral of u, it's just 1/2 u squared plus c. When you sub the tangent back in, please make sure that you are writing the trig power in the right way. You put the squared right here. Okay, two more. For this next example, example 5, this is a pretty basic one. This is just dealing with a linear piece, which has a constant for its derivative. So we know we're going to balance out some constants there. So this, our u, is just that nested function 2x minus 4. And then for du, the derivative of 2x minus 4 is just a 2. And then we attach our dx. We don't have a 2 dx, we just have a dx. So taking this equation, dividing both sides by 2, we know we're going to replace the dx with 1/2 du. So that's what I've been saying with the constants. We can always mess around with constants and kind of make them what we need to be. If there was an entire variable missing, we can't balance out a variable. And we'll talk more about that in the second half of 5-6 in the next lesson. All right, so we're going to replace everything we can here. The integral of, this is now just the sine of u, and then dx, according to this, gets replaced with 1/2 du. And just like the previous couple examples, I just throw my constant out front. So the antiderivative of sine is negative cosine. Don't forget I've got a 1/2 attached right here. And then, of course, you're going to sub back in the expression for u. Okay, so that's your final answer. So hopefully this is starting to make a lot of sense, just kind of following the procedure, rather than saying like, okay, that's my correction factor, I'm expecting to see this, I'll balance it out with this. This is kind of a surefire method that works every single time. Okay, last example for this half of the notes. I want to rewrite this, just so you know what we're dealing with here. Remember the way that trig powers work is this is actually sine of x to the 5th, so that's technically our nested function. And then times cosine. All right, so when we write it like this, kind of makes it more obvious that sine is our nested function, and then you see its derivative is present in the integrand as well. So for u, we're going to use u equals sine x. And then the derivative of u, derivative of sine is cosine dx. Okay, and we've got a cosine dx right there. We can just sub it out for a du. So our integrand becomes, instead of sine x to the 5th, we write u to the 5th. And then that cosine x dx gets perfectly replaced with a du. And then this becomes a very, very simple function. All right, so take the antiderivative. Power pops up to 6, and we divide by 6. And of course our plus c. So we rewrite and make sure you're writing it in the proper trig notation. Your 6th power goes right there. Plus c. And just like I said with the last few, you could always take the derivative of this and show that you would land yourselves right back there. Okay, so in the next section, like I said, we're going to look at some more complicated substitutions, but I want to make sure that we're actually able to just get the procedure down first before we look at anything more complicated.